Play one pure note, and the air ripples out in perfect circles. Calm, ordered. Now play a chord, just 3 notes at once, and that order detonates into this. Your ears call it harmony. Your eyes call it a mess. So how does your brain and your phone instantly pull the clean notes back out of that? The answer is one of the most beautiful tricks in all of mathematics. And to find it, you have to stop looking at waves and start looking at circles. Welcome to ThirdEye Labs, where we make the unseen seen. Today, the hidden geometry of music. In 1807, Joseph Fourier was chasing a very physical question. Heat a metal bar in the middle, and how does the warmth spread and fade? His trick was outrageous. He claimed any temperature pattern, however jagged, is secretly a sum of smooth sine waves, and sine waves cool in a way he could solve. The greats of Paris, Lagrange, Laplace, Legendre judged the paper, and they rejected it. Their objection was simple. How could perfectly round, smooth circles ever add up to a sharp corner? But watch what happens when you stack more and more sine waves. 1, 3, 6, 15. The corner appears out of pure roundness. See those little ears that overshoot at the jump? They never go away. That stubborn ringing has a name, the Gibbs Phenomenon, and it haunts every digital signal to this day. It took 22 years, and a mathematician named Dirichlet to finally prove Fourier had been right all along. 90 years later, before any computer existed, Albert Michelson built this, a harmonic analyzer. 80 brass gears, each spinning at a different harmonic, their motions summed by a lever, computing Fourier's sum by hand. The idea, though, is far simpler than the machine. Let me show you. Spin a merry-go-round and toss a ball each lap. Spin at the wrong speed and the throws scatter evenly, so nothing happens. But spin in sync with the throws, and every ball piles up on one side until the whole ride lurches. That sync is a hidden note. Here is a single pure note, drawn as a wave. Now wrap that wave around a circle, like winding string onto a spool. That gold dot is the center of mass of the coil, its average position. As we change the winding speed, watch the dot. At most speeds the coil is balanced, so the dot sits dead center. But exactly when the winding speed matches the note, the coil pulls to one side and the dot lurches out. One note, one spike. Add a second note and the wave turns jagged again. But the machine doesn't care. Wind it, sweep the speed, and the center of mass lurches twice, once for each hidden note. The fading trail it leaves behind is the spectrum, drawing itself. Those two peaks are the DNA of the sound. Winding around a circle has a tidy symbol. Euler's number E, raised to an imaginary power, is just a point marching around a circle. Multiply your signal by it, and you have wound it. Average the wound-up signal over all time, and you get the Fourier transform. Here it is. Don't let it scare you. The integral is just a fancy way of saying, find the average position of that wound-up scribble. Distance from the center is how loud the note is. That is the entire idea. Let's run a real chord through it. C major, 3 notes at 262, 330, and 392 Hz. Out come 3 clean spikes. Now we edit reality. Grab the E spike, the major third, and drag it to 0. Same air, but we surgically removed a note. Doing this naively costs n² steps. In 1965, Cooley and Tukey published a shortcut that cracks it in n log n, though Gauss, typically, had scribbled the same trick a century and a half earlier. That one speedup is the fast Fourier transform. It is, quietly, one of the most important algorithms ever written, and it's running on your phone right now. Play the very same note on 4 very different instruments, and your ear hears 4 different colors. That color is timbre, and it is nothing but a different recipe of overtones, which the transform reads in a single glance. Piano, a struck string stack. Harmonium, rich sustained reeds. Guitar, a bright plucked string. Tabla, an enharmonic drum. So far, we've only used the height of each spike, the loudness. But the center of mass is a vector, and its angle carries the other half of the story. When the note starts, its phase. Slide the note in time. The loudness never changes, the spike stays the same height, but the vector spins. Same note, different moment. Ignore phase, and you can keep every frequency, yet destroy the sound. Scramble the phases of a sharp drum hit, and the crisp attack smears into a formless wash. This is exactly why early audio AI sounded robotic, and why modern models work so hard to get phase right. Slide that spectrum along time, and you get a spectrogram, a picture of which frequencies fire and when. A melody becomes a staircase of light. This picture, not the raw wave, is what a model reads. Whisper, the speech recognizer, turns your voice into one of these and slides a window across it, the very same attention you saw in the geometry of tensors. Shazam fingerprints a song by its loudest peaks. JPEG and MP3 shrink your files by simply deleting the frequencies your senses can't catch. And Fourier neural operators learn physics itself in this domain. Different machines, one idea. Okay, now let's point this whole machine at real music and watch something that honestly feels like magic. Layer all 4 instruments into one short piece: a drone, a melody, and a beat. Fourier handed us a tangled picture of all of it at once. But which spike belongs to which instrument? They overlap, Fourier alone cannot say. This is exactly where it passes the baton to AI. A trained neural network looks at that spectrogram and learns to pull each instrument into its own clean track. Listen, just the tabla. Now just the guitar. Fourier gives the picture. The network does the unmixing. And if you want to build that splitter yourself in a few lines of Python, that's the companion lab waiting for you. So let's wind it all back up. A jagged sound, wound around a circle, a center of mass that lurches at every hidden note, an angle that remembers when each note began, and a whole world of AI that hears by looking at exactly this. So the next time you hear your favorite song, remember, you aren't just hearing a melody. You're hearing a symphony of circles, winding and unwinding, in perfect mathematical harmony. If a sound is just circles, a picture is circles in 2 directions: JPEG, blur, and how diffusion models dream. Thanks for watching and keep exploring. Next time, what does an image sound like? Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.